So where we left off last Thursday was the last thing I wrote up was when we do an experiment that is correct in this class, we always want to do a randomized comparative experiment. Now, the reason I'm writing this up again is this is not a design of an experiment. This is the ones that are done correctly. And what I mean the ones that are done correctly is we randomly do something, and what we randomly do is we randomly assign the subjects to the treatments. And then the comparative part, we always want to make sure that we want to compare treatments, right? So one more time, that's not a design, that's the type of experiment that we do here. And every one that I'm going to show you here is a randomized comparative experiment. Randomly assign the subjects, we always compare treatments, all right? So back to the one we were talking about last Thursday with that GMAT test and the online version of the course. All we had was this new course, was the online version. We didn't have anything to compare to, right? So what we're going to do is we're going to give them a classroom version also, so we can compare the online with the classroom. So we're going to end up with 2 treatments. All right? One of them is going to be the online version, which is what we're really interested in. That was the treatment we really wanted to talk about. And the second one is the classroom, so that we have something to compare to, right? That's the way the class had always been given, and all of a sudden this one semester they decided to do an online version. This group that gets this is going to be called the control group. So that we have something to compare to. Look, anytime you got one treatment that you're interested in, you always have to introduce this control group, this other group that gets the treatment that is like, think about it like being the norm, what's normally happening, so that we have something we can do the comparative part, right? So since there's only one treatment you're interested in is the online class version, we introduce this control group, we give them the classroom version, and so we can compare the online version versus the classroom version, all right? Look, this happens every time you got one treatment you want to deal with. Forget this one for a second. Suppose we got some drug. We got a pill that's supposed to control blood pressure. Obviously, we're not just going to give people the pill and see how there's nothing to compare to, right? So we come up with a control group. Yeah, and what do we give the control group? We give them a dummy pill. Anybody ever heard of a placebo? Yeah, so when you're talking about drugs and stuff like this, you give them a placebo, right? So that you have something to compare to. I mean, it looks just like all the other, looks like the pill you're given has got something in it, except it has nothing in it, right? That's what you do. You give them a placebo. Here, the control group, they're going to get a classroom version. That's what the norm is. That's what's been going on, and we're going to compare the two. All right? Now, here's what we're going to do. I want to give you an outline of this experiment where I've got these 2 treatments. And when I do an outline, I'm not going to write it out for you. I'm going to draw you a picture of what's going on. All right? So my first start is this. Let's say, for example, we have 50 students that need the course. All right? That's how many I know I got 50 students that need the course. Now, to make it an experiment, we have to pick which course they take. We don't let them sign up, right? Because remember, the ones that sign up for the online course is different than the ones that sign up for the classroom course. We want to control that. So we're going to pick. We're going to impose the treatment to make it an experiment. All right? So here's what we've got. My outline looks like this. My picture of this experiment. I've got my subjects. 50 students. Right? The first step is to randomly assign them. So we write down here, oh yeah, we're going to do some kind of random assignment. Now at this point, we're going to start making groups. How many groups do I have to have? I have to have 2 because I have 2 treatments, right? So I'm going to come up here. I'm going to give you a group 1. I'm going to come down here, and I'm going to give you a group 2. If you want to think about it, that's your control group right here. That's the one that's going to get the classroom version. Also, I can keep track of how many I'm going to put in each one. I'm going to put 25 there, and I'm going to put 25 there. Now, how would I do this? Look, we just did the previous chapter to tell me how to choose samples, right? What I'm trying to do is I'm trying to choose a sample of size 25 here. I want to choose an SRS of 25. So what I would do is I'd label my students 0, 1 through 50. Right? I'd go to table B in the back of the book and start reading them as pairs. The first 25 that I have labels for, that's going to be your first group. The last 25 is going to be your second group. So when I say random assignment, the simplest thing to do is just take a simple random sample of 25 out of the 50, put them in group 1 and the 25 that's left over in group 2. And then this here is going to get treatment. I'm going to label it treatment 1. This is the online course. This one down here is going to get treatment 2. That's your control group. They're going to get the classroom version of the course. Now, at the end of your experiment, what makes it comparative is here at the end, I come down, whatever your response variables that you are measuring, or in this case, your response variable is the GMAT score, you want to compare the GMAT score for these two groups, for these two treatments. I want to compare, let me put it here so you can see it. I want to compare GMAT score. That's an example of a randomized comparative experiment. Notice both of those words are on my outline. We randomly assign the subjects to the treatment groups. And what do we do at the end? We compare the response variable. In this case, the response variable is their GMAT score. That's the simplest randomized comparative experiment that we can get. We randomly assign the subjects to the groups, and then we compared the response variables. We compared the treatments at the end there. Now, again, one more time, and I'm going to scream this at you a couple more times here. That's a randomized comparative experiment. We randomly assigned the subjects, and we compared the response variable for the different treatments, right? We always like randomized comparative experiments in this class. Now, this experiment, this randomized comparative experiment has a design. Okay? The design of this experiment is not randomized and comparative. They are all that. The design here is called completely randomized. Now, where I'm getting this from in your book is page 235. It says, a completely randomized design. I'm looking at this little box here. In a completely randomized experimental design, all the subjects are allocated or assigned at random among all the treatments. We didn't do anything funky. It's just, you had a pile of them. You chose a simple random sample of 25 that went in the first group. The 25 that was left over went in the other group, right? We didn't consider anything. All right? So, I'm going to label this number 1. I'm not done giving you experimental designs, but that's your first one, a completely randomized design. It means you got them all right here in a pile. You randomly assign them to the treatment groups by chance. All right? Yeah, I know. It makes no big deal here at this point that, well, I've got one design. Now, here's the thing. The previous chapter, we had sampling designs. Now you have experimental designs. How do you set the experiment up? They're all randomized and comparative. Does anybody remember our 4 good sampling designs? Simple random sample, stratified, systematic, multi-stage, right? You have one experimental design at the moment. It's a completely randomized design. Yes. Does it look like a simple random sample over here? Yeah. A simple random sample is not an experimental design. That's a sampling design. Stratified random sample is not an experimental design. It's a sampling design. It's how you choose a sample. Completely randomized is an experimental design. It's how you set up the randomized comparative experiment. All right? Now, I'm not interested in example 9.6 because I'm going to do one for you later. Okay? Here's my thing. All right? I'm on page 237 in your book. And the title of this little section here, 9.5, is the logic of randomized comparative experiments. Because remember what we're looking for here. The reason we're looking at a randomized comparative experiment is because we're looking for causation. We're looking for cause and effect. We're looking to see if we change the value of our explanatory variable, does that cause a change? Does that cause differences in our response variable? We're looking for cause and effect. Now, before I get to writing down the logic and all this kind of stuff, can we come back to this picture here, this outline, for just 1 second? We randomly assign the subjects to the treatments, right? In other words, we are imposing the treatment. We're imposing that this group took the online version and this group over here took the classroom version. What's the only difference between those two groups? In other words, I got a group 1 that's got 25 students. I got a group 2 that's got 25 students. What's the only difference between these two groups in this experiment? How are they taking the class? One's getting an online version. The other one is getting a classroom version. Is there any problem here with lurking variables? Remember before, last Thursday, there was a problem with lurking variables. Remember the ones that signed up with the online class were usually older, maybe paying for it by themselves. Do I have that problem here? In other words, do I have any confounding problems here? Do I have any problems with lurking variables? And the answer is no. There's going to be older students in both groups. We assign, right? There's going to be some paying for themselves on both groups. All that. The only difference between my two groups here is the actual treatments. Yes? Okay. And then at the end, let's say I get to where I start comparing. Let's say I look at the average score for the online GMAT score, right, for the online version, and then I look at the classroom version. Let's say I take the average score for that group. Yeah? Let's say the average score for the online GMAT, for the online group taking the GMAT test is a 72. Let's say the classroom version that took the class, the average is 70. Did how they take the class make a difference? 72 compared to 70. Does anything up? See, the deal is this. This is the other thing you got to get stuck in your head for 1 second here. Is when I'm doing a randomized comparative experiment and the treatments had nothing to do with anything, I don't expect when I compare the comparison to be exact. If the online version has a 72 average and the classroom version has a 70 average, I'm telling you the class, how they took the class doesn't matter. Everybody understand that? Let's say the online version had an 80 average and the classroom version had a 60 average. Do you think the class made a difference on how they took it? The further they are apart, the more it comes down to the treatments made a difference. I expect them, if there's nothing going on with the treatments. In other words, how I took the class made no difference. I expect the scores to be close together. The further they get apart, the more the treatments had to do with it. Right? See, I don't want you to think before I start writing down the logic and all this, I don't want you to think that just because the treatments didn't do anything, that the scores are going to be exact. That's impossible. You got different individuals in the groups, right? You got different subjects. I expect them to be close. Okay? So here's the logic. Actually, I just said it to you out loud. We're going to write it down now. The logic of randomized comparative experiments. Okay? One more time. The randomized comparative experiment is set up to give us evidence of cause and effect. Causation. Right? Now, the logic goes like this. And I'm going to give you a 1, 2, and a 3 here. We do random assignment. Look, this is nothing we just didn't talk about. Random assignment. What's the random assignment do? What does it do to impose the treatment? It means we produce similar groups. And I'm talking about the groups that are getting ready to receive your treatments. They should be similar. There shouldn't be anything going on funky there. 2, the comparative part, where we're going to compare the treatments at the end, the comparative design part of it, and I don't want to use the word design, I'm just going to put comparative there. What that does is what does that do for us? It does this. The only difference between the groups are the treatments. Look, we have to have these two things if we're going to talk about cause and effect, causation, changes in the explanatory variable causes a change in response. You have to have this. You've got to have this random assignment to produce similar groups. You've got to compare treatments, the comparative part of all this, so that the only difference between your groups is the actual treatments that are being imposed. That's the randomized comparative part. Now there's a number 3 here. And number 3 is going to take a little thought here. Okay? Number 3. Differences in the response variable. You know, where we compare at the end. When we start seeing differences in the response variable are due there's a 1 and a 2. We're hoping for number 1. We're hoping to see differences that are large enough that they're actually due to the treatments. That's why we did the experiment to start with. That's what we would hope. But there's a number 2. And the number 2 is the play of chance in assigning the subjects. Now, this is what we want to see, right? We want to see differences large enough that they're due to the treatments. We want to see this. That's what we're looking for here. So what do I mean by this number 2, the play of chance in assigning the subjects? Here's what I'm going to give it to you. I got these 50 students, and I'm going to do an SRS of 25 of them and give them the online version. The other 25 that's left is going to do the classroom version. Is it possible, by me choosing a simple random sample of 25 out of the 50, that I put the best 25 students in that group? Is that possible? Yeah, that's possible. Is it possible I put the worst 25 in the classroom version? Then what happens? All of a sudden, the online version shows up as being better, but what happened? It was this play of chance, yes? So then how are we going to eliminate this idea of play of chance in assigning the subjects? Have you ever wondered why, when it comes to forget this for a second, when it comes to a drug, they don't do one experiment and put it on the market? How many times they do the experiment? They do it over and over and over again. They use many subjects, right? I mean, it takes a year's worth of trials or 2 years' worth of trials to get a new drug to come to the market, yeah? Why? Because they're not going to work off of one experiment and say, oh, yeah, the drug works. They're going to do that experiment 50, 100 times on thousands and thousands of subjects. So what happens now? Let's say the first time I do the experiment, the online class looks a lot better. Let's say I do it again. The online class looks a lot better. Let's say I do it a third time, the online class. In other words, I do it like 3 semesters in a row, and every time the online class has a much higher average than the classroom. What's that due to? Is it due to the play of chance? No. What's it due to? It's due to the actual treatment. So the way we get around this play of chance in assigning the subjects is you do the experiment more than once. You do it on many, many, many subjects, right? You do it over and over again, 2 or 3 times. You don't rely on just one, okay? Now, the rest of the stuff, I'm not going to write that down for you because I'm going to come back and give you 3 principles of experimental design, and that's going to be one of them. I want to tell you this one story one more time. Let's say we do the experiment one time. Let's say we do it 5 times. And every time it's like 7270, online version. Next time it's 7371, 7470. Is there anything up? Those are close, right? In other words, those are close. So there's nothing up. The differences I'm seeing, there's no differences. As far as I'm concerned, looking at 72 versus 70 or 73 versus 71, 72 versus 69, there's no differences, right? I've repeated it over and over again. I've seen it 3 times. There's no difference, right? So the way the treatments had nothing to do with it. Okay, let's say I do it 3 semesters in a row. The online version's an 80, 69 on the classroom version, 79, 72, 81, 65. Every time I'm seeing this over and over again, the differences are large, right? So what's up? The online class must be a better way to do it. Yeah, because I repeated it at least 3 times. What do I got? I got 150 students that we've done this over and over again, and every time I'm seeing the same thing, right? That the the online version is much better than the classroom version. All right? I just got to get that stuck in your head. You're going to see small differences if the treatments had nothing to do with it. If you have large differences, repeated, the treatments are doing it. All right? Now, here's where I'm at in your book, and I'm going to keep pointing you there tonight. I'm on page 238. Okay? On page 238, there's principles of experimental design. There's 3 of them. One is control. We restrict the effects of lurking variables on the response most simply by comparing 2 or more treatments, right? So you get control through comparing treatments. Look, these 3 go right in line with the 3 I just wrote down. 2, randomization. Which means use chance to assign subjects. Now, before I write number 3, they're telling you, when you look at principles of experimental design, you always want to do a randomized comparative experiment, right? That's what those first 2 are. Okay? The control part, that's comparing the treatments. That's the comparative part. The randomization, you're randomly assigning the subjects, right? You're using chance. That's the randomized comparative experiment part right there. Now there's a number 3. And they make it real simple. Replication. And what they say with replication is use enough subjects in each group to reduce chance variation in the results. I think about use enough subjects 2 ways. In each experiment and be able to repeat the experiment over and over again. You're not going to trust anything on 2 people, are you? No. So you want to use enough subjects in each experiment, and then I would also be able to replicate the whole experiment over again if I could. Use enough subjects. What are we ruling out with this? Why is this replication important? We're taking care of that. We're taking care of that play of chance, right? That's what we're taking care of. Yep. Okay. So these are the 3 principles of experimental design. One more time. 1 and 2 are telling you want to do a randomized comparative experiment. Number 3 is telling you need to have enough subjects. You need to be able to repeat this. Okay. On test number 2 coming up, I don't know when that is. We're getting closer and closer. This is one of the questions. Which of the following is not a principle of experimental design? Well, 3 of them are control, randomization, and use enough subjects, right? Replication. Now, I got some language for you about these differences and how large they are. Because the reason we are doing the randomized comparative experiment and being able to repeat it is we hope to see differences in the response variable so large that it is unlikely to happen by chance. Now, there's a reason why when I was talking about the online versus the classroom version, why I'm picking, if the online version has a 72 average and the classroom version has a 70, 2 points is on a 100-point scale. That's not much, right? There's a reason why I went to like 80 and 68. That's a large difference, right? 12 points on a 100-point scale, that's large. That's what we're hoping for, right? We want to see differences so large that it can't be due to just chance. In other words, we're looking to see for differences so large that something has to be going on, that the treatments have to be making a difference. All right? So nobody writes it like this. Oh, yeah, you know, my differences are so large they were unlikely to happen by chance. That's not statisticians' language. Sorry. That's what we're hoping to see, but that's not the language they use. The language they use is statistically significant. Oh, and this won't be the last time you get to hear me say those words. Statistically significant is on page 238. That is just a fancy way of saying that the differences are so large that they can't be due to chance, that they're unlikely to happen by chance. In other words, I'm on page 238. An observed effect so large. In other words, the difference between your treatment groups is so large it would really occur by chance is called statistically significant. Statisticians will tell you this. The results of your randomized comparative experiment are statistically significant. In other words, the differences are large between your treatment groups. They're so large that they could not have happened just by chance. It's like an 80 and a 68, folks, not a 72 and a 70. That's how they say it. Now, when somebody tells you the results of the randomized comparative experiment are statistically significant, what they are telling you is the differences are due to the treatments. Bingo. That's the reason we was doing it to start with. In other words, one more time, when somebody tells you, you know, the results of my randomized comparative experiment is statistically significant, that's a fancy way of telling you that the difference are due to the treatments. You know what else they're telling you? We have evidence of which is where I started this chapter. If we have an experiment, randomized comparative experiment, and the results are statistically significant, the treatments actually played a role here, right? In other words, we have evidence of causation. We have evidence of cause and effect. As soon as it's statistically significant, the treatments did something. In other words, the treatment groups were different. The differences were large enough to say they couldn't have happened by chance. We have evidence of causation. Now, here's one warning, all right? Everybody look at me for a second. On page 238 in that definition, an observed effect so large, I can't tell you how large needs to be yet. I will, before the semester's over, tell you how large it needs to be, but I knew if I told you I had a 100-point test and an 80 and a 68, you would tell me from 80 to 68 that would be large, right? I can't tell you how large it is. All I'm giving you is the language of this at the moment, that we want to see statistically significant results. That means the treatments had an effect. That means you have evidence of causation. All three of these things right here mean exactly the same thing, except that's a statistician's language. Oh, your results are statistically significant. What's up? The treatment's made a difference. Ah, I got evidence of cause and effect. I got evidence of causation. That's what they're talking about here. Okay? Now, that's a randomized comparative experiment. That's the logic. That's the principles. That's the language for when we actually find something. And what I mean is we found this evidence of cause and effect. Now, the next little section here is cautions. All right? So I have a couple cautions for you. Look, we know we're going to do randomized comparative. Even if we do that, there's a couple things to pay attention to here, right? The first one is something called the placebo effect. Does anybody know? We just had to talk about a placebo, right? That's like a dummy treatment. Has anybody ever heard of the placebo effect? Where people respond favorably because they're getting any treatment? Yeah? Right? So to combat that, the placebo effect, you give them a placebo, right? So a placebo is a dummy treatment. The reason I wrote control under that, when I say dummy treatment, I mean it might be what the norm is. It might be a pill that looks like the pill that everybody else is taking, right? So that they're not thinking, well, I'm getting the real thing or not getting the real thing. Yeah, so I got a little story. That's the first caution. Beware. Now, this is only happening where you're dealing with humans and you're dealing with some kind of drug treatments, right? Or drugs, right? Where you got some of your treatments or you want some pill or some kind of drug to do whatever. Well, I'm a Copenhagen user, right? So my wife thought I should quit. Yeah, my wife thought I should quit. So you ever seen those nicotine patches? You know, you can buy them nicotine patches for like $80 in a box. So she bought me some. Now, needless to say, it must not have worked because I still got that Copenhagen in my pocket. But what was interesting to me is not what's on the outside of the box. Hell, you can go to next time you go to Walmart, pick up any kind of medication or whatever, like for colds or whatever, and read the back. You'll see all kinds of good shit. You'll see they did a randomized comparative experiment. Ooh, they gave a placebo to control for the placebo effect and all this. Yeah. Well, it said that same stuff on the back of my little box of those nicotine patches. Yeah. So the problem was on the outside of the box, they just gave me the language that made me feel comfortable. But I had to open the box because I was actually thinking about sticking one of them on me. But there's a little pamphlet on the inside. There's a reason why this one was on the inside of the box. And on the inside of the box, it turns out that 51% of the people that was given the real treatment quit smoking. Yeah. But like 42% of the people that took the placebo quit smoking. You understand why that was on the inside of the box when it was an $80 box, right? Yeah. So you might want to know those little things up front. Now, here's the thing. If anybody wants to quit smoking, I got some patches upstairs. I only charge you $40. Well, hell, I mean, I got a 42% shot at getting you to stop, right? Whether you know what the hell it is or not. They never put that little placebo effect percentage on the back. They say, oh, yes, this is placebo control, but they didn't tell me on the back of the box before I bought it that 42% of the people that had the placebo quit smoking. A little story about the placebo effect. People respond to any treatment if they think they're getting the real thing. We give them a placebo, a dummy treatment. That's usually your control group, right? Placebo effect. Okay, so there's one other way I can screw up a randomized comparative experiment. This is one way. The second one is actually how we do things. And there's something called the double blind technique. Yeah, I got a story about this one too. Because that'll show up on the box too. Oh, yeah, we did a randomized, comparative, placebo-controlled, double-blind experiment. All of them. All the magic words we teach in this class. It's on the back of the box. If you don't like the nicotine patches, anybody ever take those little lozenges, those little like pills for cold and little zinc tablets? And nobody tried them? Nobody got suckered in? I don't know. Next time you go to Walmart, read the back of the package. You'll see all the magic words. They got my wife. Yeah, she come home with these things, right? Zinc tablets.
I don't know, like the airborne.
Oh no, this is like it looks like a cough drop. And it turns out, if you take these, then the severity of your cold will be reduced by like 72%. Well, how in the hell did you know how bad my cold was going to be before I started? I couldn't get an answer out of her on that when she bought them. So now whenever I start getting a sniffle, I just go run and get one. Hell, I'm going to get better quicker. Okay. Double-blind technique. What this means is, okay, you got somebody here and you're handing out the pills, right? So obviously the person getting the pill doesn't know whether they got the real pill or the dummy treatment. That would defeat my number one, right? Well, with me, if I'm handing out the pills, you can't let me know either. Because I'll be giggling at you getting the dummy treatment, right? So I would be tipping them off. So double blind is the person getting it doesn't know whether they're getting the real deal or not. And obviously the person giving it doesn't know. Well, then the students always look at me at this point and say, well, look, if the person getting it doesn't know whether they're getting the treatment or the dummy or the placebo, the person handing them out doesn't, you understand the guy in the back room there that handed the pills to you, he knows which is which, right? So somebody knows. It's just the person giving it to you and the person receiving it doesn't know, right? That's double blind. What are we controlling? The placebo effect again, right? Okay? Now, that's my two biggies here. And I got a third one that you need to be aware of. And I'm going to look at the example in the book for this one. But there's a number 3, and it's a lack of realism. Yeah, you wouldn't think this would be a problem, right? That, you know, whatever you're experimenting doing doesn't actually translate. But I'm on page 240, and I'm looking at example 9.8. And then I'm going to bring you up a little more current than what this one is. It says that those high center brake lights required on all cars sold in the United States since 1986. And I would have thought this guy would have updated this by now because I'm looking everywhere. The hell, most of you people weren't even born in 1986. Well, you didn't even know there was such a thing as a car that didn't have that red light shining in your eyes when you stepped on the brake in front of you, right? No, it used to be. Cars didn't have that light in the back window or on the trunk or wherever in the hell it is to try to make you stop now. It didn't used to be there. And so what they did was they did an experiment. They said, okay, randomized comparative experiments with fleets of rental and business cars done before the lights were required showed that the third brake light reduced rear-end collisions by as much as 50%. In other words, something was up, right? I can remember because I started driving in 82. Yeah, when I first started driving, there wasn't no red light in the middle. It was just them two down here. Now, all of a sudden, you got one staring at you. You're like, shit, I should stop. You stepped on the brake and stopped, right? But what happened is after they were required on all cars, they only stopped them by 5%. What happened? We get used to it, right? Yeah, you guys don't even see that red light in the back of the window. So what do they do now? Now that little red light moves across the back of the window, doesn't it? Don't your taillights have little red things on them? What's the newest thing? Isn't there little turn signals on your mirrors? Yeah, somebody tested that and thought, yeah, we put these turn signals on the mirrors, it'll stop people from running over people when they're turning. You know what happens after all the cars have those? They don't make a difference because they all have them, so you just say, the hell with it. All right? That's the lack of realism. When it's new, it catches your eye. After everything has it, we wasted our time putting them there. Okay? Now, there's two things left here. What's my first experimental design? What was the one I talked about tonight? Completely randomized, where you can assign them completely at random to your treatments, right? Well, now I have two more. And I'm going to label these experimental designs. It's how your experiment is set up. Number 2. Remember, number 1 is completely randomized. Big pile, assign them at random. Number 2 is matched pairs. Now, The problem with matched pairs, before I go into it too far, you can only have 2 treatments. Completely randomized, I can have 32 treatments. As long as I got enough subjects to make 32 groups, I can have 32 treatments. Matched pairs, you're only allowed to compare 2 treatments. That's it. All right? What you do in matched pairs is you match the subjects as pairs. Now, I don't know what variables we're going to be interested in. Do I want to match them by their gender, by their age, by their education level? But what you do is you have all your subjects and you match them up in pairs. Right? By whatever variables that somebody's interested in their experiment. Maybe it's, like I said, gender, age, whatever. So when you're sitting here, you have all these pairs that are matched as close as possible. Right? That's what your experiment starts looking like. What you do is you give one individual in your pair treatment and you give the other one a treatment, and then you compare the treatments on that pair. This is a randomized comparative experiment because how do I decide on, here's my pair, which one gets the treatment? Flip a coin. If it's heads, this one gets treatment 1. If it's tails, this one gets treatment 1. You do that for every pair. So that's the random part. Where's the comparative part come in? Well, I've got each pair. This one's getting one treatment, this one's getting the other, and I'm going to compare the treatment within those pairs. That's a matched pairs. If you don't match the subjects as pairs, or you treat each subject as a pair. In other words, take every subject, flip a coin. First, if it's heads, are going to get treatment 1 first. If it's tails, are going to get treatment 2 first. All right, they get treatment 1. You wait, you give them treatment 2, and then you compare the results of those treatments on that one particular individual. So they're matched. When I treat every individual as a pair, they're matched as close as possible, right? That's also matched pairs. So you can match them up, 2 treatments, one person, first they get one treatment, and then they get the other treatment. Those are both randomized comparative experiments. It's how we set it up. It's the design. How did we get this started? So we come over here and we look at example 9.9, cell phones and driving. Okay? It says, do you want me to go back to about the brake lights and tie 9.8 into 9.9 for you? If I didn't have those cell phones, I wouldn't need that big red brake light in the middle of the window. Okay? It says, does talking on a hand-free cell phone distract drivers? I don't know. Undergraduate students drove in a high-fidelity driving simulator equipped with hands-free cell phone. The car ahead brakes. How quickly does the subject react? Let's compare 2 designs for this experiment. There are 40 subjects available. They're going to compare completely randomized with a matched pairs design. One is better than the other here. It says, in design 1, the completely randomized design, all 40 subjects are assigned at random, 20 to simply drive and 20 to talk on the cell phone while driving. In design 2, the matched pairs that was actually used, all subjects drove both with and without. So when they did the matched pairs, they treated each subject as a pair. One day they drove with it, and one day they drove without it. We flipped a coin to see which one went first. All right? The 2 drives are on separate days to reduce carryover effects. That's for the matched pairs. The order of the 2 treatments is assigned at random. 20 subjects are chosen to drive first with the phone, and the remaining 20 drive without the phone. That's still the matched pairs. Some subjects naturally react faster than others. See, here's the thing. Let's think about the completely randomized. I got 40 subjects. 20 of them is going to drive with the phone, and 20 of them is going to drive without the phone, right? And then at the end, I'm going to compare this group's reaction time with this group's reaction time. What's the problem here? You're comparing my reaction time with your reaction time. Well, hell, my reaction time might be slower than yours to start with. I'm trying to compare apples and oranges, right? My reaction time with a phone to your reaction time without a phone, well, hell, my time and your time is different either way, right? What about with the matched pairs? First I drive with it, reaction time. Then I drive without it, reaction time. I'm comparing my reaction time to my reaction time, right? I'm comparing apples and apples with the matched pairs. So the only way to do this is with the matched pairs. Right? I don't want to compare my reaction time with your, ours is already different. So that doesn't do us any good. That's an example of both of them. All right? Now, there's a third one. There's a third experimental design. And the third one is something called a block design. It is still a randomized comparative experiment. It's a block design because what you're going to do is we're going to divide the subjects into similar groups called blocks. I have a question for you. Where have I done this before? Where have I taken my individuals and divided them up into similar groups? Anybody remember? That's a stratified random sample, right? We divide the population up into similar groups and then sample each one. Well, here, with the block design, this experimental design, we're going to divide the subjects into similar groups, and they're called blocks. Then you're going to do the randomized comparative experiment on each block. Now, the reason we would do this, okay, is because groups of subjects react differently to the treatments. And we know this ahead of time. We know that there's different groups of our subjects that's going to react differently to the treatments. You know that up front, right? So look, this idea of a block design, this idea of these blocks, this is just another form of control. See, we know this little fact up front that there are different groups in our little subjects here that are going to react differently to the treatments, and we bring that into the experiment in the form of these blocks. Now, there's a couple places I can think of real quick where this happens. The example I'm going to look at in the book is advertising. Women react different to different types of advertising than men do. It also turns out that for certain types of cancer treatments, that men and women react differently to them. Right? So you want to bring that into your experiment. Because if we do that, and you know this up, look. All right, time out. Anytime I got more information up front before I do anything in this class, the better off I am. Right? With an experiment, that's no difference. So if I know something up front, like men and women are going to react differently to certain types of advertising, I want to bring that into the experiment. Or that I know men and women are going to react differently to different treatments for cancer, whatever kind of cancer it is, I want to bring that into the experiment. Blocks are another form of control. It's bringing that difference into your experiment. All right? So here's what they've got. Women and men respond differently to advertising. An experiment to compare the effectiveness of 3 advertisements for the same product will want to look separately at the reactions of men and women as well as to assess an overall response to the ads. A completely randomized design, we're just going to throw them all in a pile. You're going to have 3 treatment groups, and then we're going to go, right? I want to look at the block design of this, and I want to give you an outline of this. Just like I drew that picture before, and my outline is of a block design. Last time it was a completely randomized design. Now, we start the same. We start with our subjects. Now, you remember before, my first move was to do the random assignments and make the groups, right, and completely randomized. But we're looking at 3 different advertisements, and we know that men and women are going to react differently to them. So we're going to bring that in, and what we're going to do is, the first move is, get your men, get your women. There's your blocks. There's nothing random about that. Right? You just divide them up because you knew something up front. Now, I just told you, you're going to do the experiment on each one of the blocks. So here, I got 3 treatments, right? I got 3 advertisements, so I need 3 groups. So I'm just going to do this. We're going to do 1, 2, 3. I'm going to label that group 1, group 2, group 3. I don't know how many men or women I have here, and I don't care. I'm just setting this up for you. And then we're going to do this random assignment. Now, same thing with the women. You're going to have 3 groups. A group 1, a group 2, and a group 3. Now, how do I get that random assignment? You got the men. Label the men 0 whatever to however many it is. Pick the first whatever it is for the SRS or so many go here, the next exercise goes here, and the next one goes there. Still just a simple random sample, random assignment, chance. Do the same thing for the women to get these 3 similar groups. The groups should be equal, right? They should look the same. Then this one here is going to get, now I'm not going to write treatment. I'm going to actually write what's there. And what you're going to get is, this one here is going to get add 1, add 2, add 3. This one here is going to see add 1, add 2, and add 3. Those are your 3 treatments for each one of them. Okay? And then at the end, we're going to compare their reaction. And what I mean is this. You're going to compare the reaction of the men to the advertising, and we're going to compare the reaction of the women. So what we did is we did the experiment on the men, and then we did the experiment on the women. We brought that in because we knew something up front, that men and women react differently to advertising. Is this a better way to do it? Knowing that little fact at the beginning? And the answer is, yeah. Let's just say, for the sake of things, that the men preferred add 1. All right? Let's just say, for the sake of things, that the women preferred add 2. What should you do with add 3? Throw it away. You don't need to be showing that, right? See, a block design will allow you to draw a conclusion about each block. For the men, I'm thinking, okay, I see that add 1 is better, right? They reacted better to add 1 than they did 2 and 3, yep. For the women, inside of that block, they reacted best to add 2. Add 3, you was wasting your time. Neither one of them liked that one. All right? You do understand that if we did a completely randomized and put all the men and women in a pile and made 3 groups, that we might miss this, right? You would never know that the men preferred this one and the women preferred that one. So it allows you to draw separate conclusions. And then when it said, I can get an overall conclusion, well, my overall conclusion is, don't show add 3. When would you like to show add 1 if you were the advertiser and you knew that men preferred it? Oh, I'm going to stereotype like a madman right now. When should you show add 1? Sundays, during football, some sporting event for me, right? Now, the ladies, I'm not going to mention that because I don't know. Sometime when you guys watch TV, that's when we should show add 2. Yeah. When should we show add 3? Never. Right? So did we draw an overall conclusion about everything? Yeah. Men want to see 1. Women want to see 2. Nobody wants to see 3. It's another form of control. Right? You're controlling, and what we're controlling here is that men and women react differently to advertising. Now, I would start drawing lines all over this. You understand, we did a randomized comparative experiment on the men, a randomized comparative experiment on the women. As soon as you see them take their subjects, start dividing them up into similar groups, you're looking at a block design. Now, I'm going to come back to this page just one second. Does anybody understand that match pairs is just a very fancy block design? Each block either has one individual in it or a pair. Yeah. Block design, you can have as many in each block as you need, or whatever you have to work with. All right? Now, I'm going to scream at you one more time, because as far as I'm done with this. Okay? Chapter 8, Chapter 9. Sampling, experiments. 4 good sampling designs: SRS, stratified, systematic, multi-stage. 3 experimental designs: completely randomized, matched pairs, block design. When somebody asks you how they chose a sample, do not tell me block design. When somebody asks what was the design of this experiment, 2 things you don't tell me. You don't tell me stratified random sample, and you don't tell me randomized comparative. That is not a design. All our experiments are randomized comparative. Experimental design is talking to you about how did you set the randomized comparative experiment up. Did you put them all in a pile, allocate them at random? Did you match them? Did you make blocks and do the experiment? That's what they're asking you for experimental design. Because in December, when that question shows up on your test, and I mean on the final, or even it shows up this next, I get to come to your house. Because if somebody asks you, what is this? You're looking at an experiment. What's the experimental design? And you write down randomized comparative, I get to come to the house. That's not a design. They're all the good ones we do are randomized and comparative. It's either completely randomized, matched pairs, or block design. And one other thing I get to come to the house on, if you give me a sampling design for an experimental design, or you give me an experimental design for a sampling design, I get to come to the house then too. I'm not going to come to the house, we're just going to sit there and talk, but I'm going to come to the house. All right? You don't do that. Now, with all that said, I'll give you completely randomized looks like an SRS. Right? Block design looks like a stratified. Yep. I'll give you that. But they don't go across the chapters. All right? Like I say, that's the end of my little thought here about experiments. We're getting ready to change parts of the book. What was that? Chapters 8 and 9, right? Sampling experiments. That was how we produced data. Yep. So now we're getting ready to go to, I was looking at this earlier. I don't know what chapter is next numbered. Chapter 10 is something that I'm not interested in. What was it? Data ethics. Ooh, I'm not interested in that. Chapter 11 is a review of chapters 8 and 9, producing data. What I'm interested in, and what you're going to see me, maybe I always look excitable and sound excitable and I'm loud and stuff, but now we're going to the other part of the title of the class. Remember, it was statistics, probability, and statistics. You ain't seen no probability yet. That's where we're going. That's what chapter 12 is. So we're going to talk about probability. We're going to talk about dice, cards. We can talk about the roulette table if you want. I mean, statisticians in my department always get excited when I get to this chapter because you tell me chapter 12 and you want to talk about introducing probability. Well, to statisticians, they start thinking about statistics and stuff. Well, I start thinking about gambling. Because you say probability, I'm thinking, you want to gamble, right? I mean, why else would I be interested in probability other than the fact that I want to know what's the chances I win that game if I play that? That's the way I think about it, right? So, it is what it is. Now, here's the warning. And it's not a bad warning. For us to continue at this point, and what I mean is for us to finish through the semester, we need some probability. Not a lot. We're not going to get crazy. You know, there's 2 or 3 chapters here we're going to look at, and that's all. I mean, I'm going to do it my style of things and give you my language in the book's language. But we need probability to continue. Because here's where we're at. All right? I got a population I got a question about. The population's too big. It's too large. I can't deal with the population, so we choose a sample. We know how to do that now, correct? One of our probability samples, one of our good sampling designs. And I actually ask that question to my sample. Yeah, and I get an answer there. Then I want to take that and infer back. For us to make that little loop back from the sample to the population, we need probability. So that's the reason all of a sudden we've done up to chapter 9 and we stop, and now we're going to talk about the other part of the class, probability, because we need that to continue. Okay? So, where I want to start with is example 12.1. Because this is like a typical kind of question that we want to answer. It says, what proportion of all U.S. adults own a gun? Now, my first question is, when we look at all U.S. adults, are we going to ask each one of them if they own a gun? That's your population, right? Your population here is all U.S. adults. You understand that's a very large group. Yes, millions and millions and millions. Yep. So we're not going to ask everybody. So what's our move? Our move is to, let's take a sample, right? So here your population is, just so you know, is U.S. adults. Okay? Too big. Can't ask them all. We need a sample. It says, we don't know, but we do have results from the Gallup poll. We trust Gallup in this class. They usually take random samples. We trust them. If you want to see how Gallup takes a sample, type them in Google, go to Gallup's site. They'll tell you exactly how they find their random samples. Gallup took a random sample of 1,005 adults. You see that? That's your N. 1,005. That is your sample. Notice it doesn't say simple random sample stratified, but it says random, which is our magic word here, right? So we've got 1,005 adults. They actually asked that question to that 1,005, and it turns out 342 own a gun. Really? That's all? Must not be Tennessee or West Virginia where I'm from. Okay, so now you understand that part right there is about the sample, right? They asked a 1,005, do you own a gun? 342 said yes. I own a gun. Yeah. We get a sample proportion. Look, we like to stick words like sample and population on things so you know we're either talking about the population and we're talking about the sample. We get a sample proportion. In other words, if you've got 1,005 adults and 342 of them said yes, they own a gun, what proportion owns a gun? You take the 342 and you divide by the 1,005. Yes? Everybody good? 342 out of the 1,005 own a gun. So the proportion is 342 divided by 1,005, which is 0.34. Now, nobody wants to hear that your sample proportion is 0.34. What do we do with that number? Oh, you got a proportion. Everybody's going to tell you 34% of your sample own a gun. People don't want to hear about 0.34. They want to hear about 34%. Yeah? So they always going to move the decimal place to the right, put the little percent sign. Okay? Now, if the sample was a simple random sample of adults, which is where we started sampling, then all adults had the same chance to be among the chosen. Is that true? Remember, that's one of the little facts about a simple random sample. It gives every adult the same chance of being selected. In other words, did we leave anybody out? Is there any kind of undercoverage here or anything like that? No. They gave every adult a chance, right? Okay? We didn't leave out any groups. It would be reasonable. Nah, we got nothing else. It would be reasonable to use this 34% as an estimate to the unknown proportion in the population. So, I'm going to put it in my language. We want to use 34% to estimate the percentage of all adults that own a gun. Now, does everybody understand what I got written there? I mean, I know you can read the words. We want to use the 34% that we got from our sample to estimate the percentage of all adults that own a gun. We want to use what we just learned from our sample, that 34% of our sample own a gun, to estimate what we wanted to know about the population of all adults, right? The proportion or the percentage that owned a gun. I converted everything to percentage here. So, since we would have a random sample, we would expect our sample to be representative of the population. So it seems like a heck of a good idea to use that 34% to estimate the percentage of all adults that own a gun in the United States, right? That seems like a reasonable thing to do here. It says, it is a fact that 34% of the sample claimed to own a gun. The 34 was calculated from your sample, so they did answer that question as, yes, I own a gun, right? We know because Gallup actually asked them that. We don't know what percent of all adults own a gun. See, this is your unknown. We don't know that part. That's the part about the population. This is my little circles I drew when we were sampling. We want to know what percentage of portion of adults own a gun. We took a sample, 34%. Now I want to go this way. I want to use that to go back. It says, but we estimate that about 34% did. This is a basic move in statistics. Use a result from a sample to estimate something about a population. No, this is our move in statistics. This is one of the things we want to do, and we want to do this. We're going to do this quite a bit. Use something you calculated from a sample to estimate something that you want to know about a population. Now, does everybody understand the following? If we took a different sample, in other words, do it again. Take a different random sample, 1,005 adults. We get a different result. In other words, the first sample gave us what? 34%. The second sample might give us 36%. The third sample might give us 40%. Right? Every time I take a different sample, I'm going to get a different result here, right? I'm going to get a different percentage in my sample that actually owns a gun. Right? The other thing you need to get in your head is, when I go to estimate back that 34% of those sample and go back to the population, you understand that not exactly 34% of the population owns a gun, right? Not 36%. None of those are going to be exactly right. So every time I take a sample, I get a different percentage. And every time I try to use my percentage to go back, I'm never exactly correct. Right? That's what I'm trying to tell you here. You're going to get a different result. Now, the thing about it is this. And I'm going to go over here to page 278 for a second. It says, what if Gallup took a second random sample, 1,005 adults? The new sample would have a different people in it. You wouldn't get exactly 342 that said yes. You wouldn't get 34%. Everybody understand that? If you're going to do that, you're going to get a different answer. Okay? Could it happen that one random sample finds 34% own a gun and a second random sample finds 56 that own a gun? Random samples eliminate bias from the act of choosing a sample, but they can still be wrong because of the variability that results when we choose at random. In other words, what they're saying is, one gave you 34 and another one gives you 56? Is that possible? Is it possible all of a sudden you took a random sample, you got a whole bunch of gun owners in there? Yeah. Right? You don't know if you're right or not. Okay? I don't know if the 34 is right, the 56 is closer to what's right. I don't know. I mean, it's possible when you chose a random sample, everybody had a gun. I don't know, right? Because they're random samples. Then it says this. If the variation when we take repeated samples from the sample population is too great, we can't trust the results of any one sample. Of course you can't. But how many samples are we going to actually take? You're only going to take one. You're not going to do this over and over again. It says, this is where we need facts about probability. We need probability to continue. We have to have it. We have to have these laws of probability. We need probability to continue because, one could be 34, one could be 56, one could be 42. What can we say about it then? Right? We could be all over the place. It says, now I'm going to read the rest of this to you here, all right? It says, because Gallup uses chance to choose its samples, the laws of probability govern the behavior of the samples. And what it means is this. As I move from one sample to the next, that little proportion that own a gun changes, right? 34, 42, 16, whatever it is. There's that sampling variability, right? When I go from one sample to the next, the proportion that owns a gun and the percentage that owns a gun changes. Yes? Okay. Gallup says that the probability is 0.95. I don't know if this is good or bad at the moment. That an estimate from one of its samples comes within plus or minus 4 percentage points of the truth about the population of all adults. Now, they're giving you a range, right? So they're saying, give me any sample there's a 0.95 probability that it's just within 4 on either side of the truth. So if they got 34, they're saying between 30 and 38, there's a 0.95 probability that the truth is between 0.30 and 0.38. I'm not worried about the plus or minus 4 at the moment. What I'm interested in is 0.95. Is that a good probability or a bad one? I mean, is this highly likely to happen or is this highly unlikely to happen? That's what we're interested in. I'm interested in the language of probability. That's what this chapter is about. We want the language of probability. That's what chapter 12 is. Okay? So here's my thing. It says the idea of probability. Now, I'm not writing very much at the moment because there's not a need for me to write very much. When I think about the idea of probability, I'm going to start with the simplest thing I can think of here. All right? When I think about probability, what I think about is chance behavior. Random behavior. And what it says is, and I'm looking on page 278. Yeah, I'm going to read to you a little more. It says, chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. Now, I'm going to give you the simplest thing I can think of. Tossing a coin. Right? What does it mean? So when I tell you that tossing a coin, it exhibits chance or random behavior. What does that mean? When I flip a coin, can anybody tell me whether heads or tails are going to show up? No. That's what it means to be unpredictable at any time you toss or any trial. What about if I flip that coin 100 times? Anybody going to get a pattern here? What do you expect to happen? In other words, anytime you flip it, you can't tell me whether heads or tails are going to show up. But if I did it 100 times and every time I flipped it, I wrote down heads or tails, out of that 100 times, how many times do you expect to see heads? My man's saying roughly 50%, right? You wouldn't be unhappy with a 49, 51, 48, 52, 50, 50, right? The coin's still fair. You're saying roughly 50% of the time I would expect to see heads shows up. That's what it means to have a predictable and regular pattern when you do it over and over again. Tossing a coin, right? That's what that means. And that's exactly what they're going to give you here in 12.2. I'm going to do it like this. I want you to focus on this graph and figure 12.1 on the top of the next page there. They've done the coin tossing twice. What they do is this. They tossed the coin once and they wrote down heads or tails. They tossed it again, they wrote down heads or tails. Right? Every time they toss it, they calculate the proportion of heads. So if they toss it the first time and it's heads, the proportion of heads out of the first one tosses is 1 out of 1, which is 1. They toss it again. If the next one's heads, it's 2 out of 2, it's still 1. The next one's tails, 2 out of 3, now it's 0.67, right? So every time they toss it again, they calculated a proportion of heads, right? So what you see is, you see the one that's in black there? That's the one I just described. The first one was a heads, proportion of heads was 1. Second one's a heads, proportion of heads is 2. Third one was a tail, proportion of heads is 2/3, right? Then they kept doing it. And every time they tossed a coin, they recalculated the proportion of heads out of however many tosses they did. What happens when they got out to about 50 to 100 tosses? What happened to the proportion of heads? It settled down to, what's that line on the graph? 0.5. Yeah? What about the red one? They started all over. They flipped the coin. The first time it must have been a tails. How do I know that? Because the proportion of heads is 0. The next one must have been a heads. A tail and a heads, the proportion of heads is a half. What happens to the red ones when they get out about 50? It settled down to be 0.5. That picture right there, that graph, is showing you this chance, this random behavior of tossing a coin. At any stage, you can't tell me whether heads or tails is going to show up. But does it show up to have a pattern after you do it over and over again? Yeah, about half the times head shows up, so that means about half the times tail shows up. Yep? Okay. If you don't like example 12.2, take a look at 12.3. We got some guys wasting time here. The French naturalist Count Buffon tossed a coin 4,040 times. Result, 2,048 heads, a proportion of 0.5069. That's what you're expecting, right? Around 1900, the English statistician Carl Pearson heroically tossed a coin 24,000 times. Carl Pearson didn't have anything else to do, right? And he got like a proportion of 0.505. Now, the only guy that had an excuse is the last one. While imprisoned by the Germans during World War II, the South African mathematician John Carriage tossed a coin 10,000 times. He had time on his hands. 5,067 heads, a proportion of 0.5067. So there's these people, and they sit there and toss it. I should make you go home and toss the coin 5,000 times. Count up the number of heads. What's your proportion going to be close to? 0.5. It's going to be close to 0.5, right? Yeah. Yeah. My man over here wouldn't do it. Yeah. I understand. Now, on page 279, two definitions. One, what does it mean to be random? Two, probability. I'm not going to write them down for you because they're right there. It says, we call a phenomenon, tossing a coin is a phenomenon, random if individual outcomes are uncertain, but there is nonetheless a regular distribution of outcomes in a large number of repetitions. In other words, you can't tell me what's going to happen at any time you do it, but if we record them over a long period of time, they'll settle down to a regular distribution of values, a regular pattern. The second one is the probability of any outcome of a random phenomenon is the proportion of times that outcome would occur in a very long series of trials. Now look, that's the definition of probability for us in this class. In other words, you got to observe it. In other words, probability is empirical the way we talk about it, right? When we think about probability in this class of an outcome of some random phenomenon that's showing this chance or random behavior, it's empirical. So, now, the thing is this, is that I will write that down that it's empirical, means it has to be observed. If you want to know what the probability of his head is showing up when you toss the coin, you got to toss the coin over and over again, a couple thousand times. Now let me ask you this. Suppose I pull a coin out of my pocket here, and I ask you, if I flip this, what's the probability of heads? How many faces are heads? 1. How many possible faces are there? 2. What's the probability? 1 out of 2. Me explaining it to you like that is theory. The way our book attacks it and the way it looks best for us and the way it goes best for us is that it's empirical. It actually has to be observed. This random phenomenon needs to be done over and over and over again so we can actually observe, see what the probability is. Now, I'm going to go between both of them. Right? I'll go between this idea that probability is empirical, you've got to observe it, and the theory of it. Oh yeah, there's two faces on a coin and one of them is head, 1 divided by 2, 50%. Yep. The other thing I'll do is this. You understand, like, probability is like a point something, right? Like a 0.5. Nobody ever points probability as 0.5. The way they'll tell you it's a half or 50%. They convert it into a percentage or a fraction. Okay? The only thing I have left here for tonight is I want to go to page 281. And I want to look at problem 12.2. Okay? It says, probability is a measure of how likely an event is to occur. That's all probability is. It's a measure of how likely something is to happen. Or if you like, how unlikely something is to happen. Yeah, Rob, go ahead and do that, please. Match one of the probabilities that follow with each statement of likelihood given. The probability is usually a more exact measure of likelihood than is a verbal statement. No. The number is always more exact than some verbal statement. It says, A, the event is impossible. It can never occur. What probability do you want to assign to that? It never happens. So if you do this random phenomenon 10,000 times, this outcome never shows up. You got 0 divided by the number of times you did it. Your probability is going to be 0, correct? Part B, the event is certain. It will occur on every trial. My man's pointing 1 at me. Those are the extremes. If it never happens, it has a probability of 0. If it always happens, it gets a probability of 1. Part C, the event is very likely, but will not occur once in a long sequence of trials. Do you want a number close to 0 or a number close to 1? 1 always happens, 0 never happens. This one in part C is, it's very likely. You want 0.99, right? Okay, I got time. We'll come back. We're going to talk about, if you don't know about cards, you know that there's 52 cards, 26 reds, 26 blacks, 13 diamonds, 13 hearts, 13 clubs, 13 spades, 4 twos, 4 threes, and so on. If you don't know about dice, you know there's 1 through 6 on each one of them. You might want to take a look at them before Thursday. Be careful going to the house. Get your stuff back.